NASA confirmed Thursday that the Voyager 1 probe has made history by becoming the first human-made object.
What if the space between stars isn't empty at all, but alive, structured, and possibly whispering messages across the galaxy? Voyager 1, the farthest object humanity has ever sent into space, has just picked up something scientists can't fully explain: a repeating signal deep in the interstellar void. It's not noise, it's organized. And it might change everything we thought we knew about the universe. What exactly did Voyager 1 find out there, and why are researchers around the world scrambling to understand it? In a development that has taken both scientists and space enthusiasts by surprise, NASA has confirmed that Voyager 1 is once again sending usable data back to Earth. This comes after a period of silence and uncertainty, and it marks a significant moment for the spacecraft that has become one of humanity's most enduring and far-reaching creations.
NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
Voyager 1, launched in 1977, is the farthest human-made object from Earth. It's been traveling through space for nearly 5 decades, having already passed through the outer boundary of the solar system into interstellar space. This region, beyond the influence of our sun's solar wind, is still largely mysterious. Until recently, little was known about its nature, structure, or the kinds of phenomena that might occur there. The confirmation that Voyager 1 is sending intelligible data again has reignited interest in its mission. After all, the spacecraft is operating on a tiny amount of power, less than that of a typical household light bulb. Its instruments were designed in the 1970s, yet they continue to function in conditions far more extreme than what was originally planned for. NASA engineers had been closely monitoring Voyager 1's signal. While the probe had continued transmitting over the past several years, much of the data it sent was either corrupted or nonsensical. However, after months of painstaking analysis and recalibration of systems from millions of miles away, they managed to retrieve structured, coherent information. This achievement alone is a testament to the resilience not just of the spacecraft, but of the teams supporting it back on Earth. What truly caught the attention of researchers wasn't just the fact that the probe had resumed proper communication. It was what the probe had detected that made headlines in scientific circles. The data revealed the presence of a structured wave pattern in the plasma environment surrounding Voyager 1. This wasn't just a blip or a one-off signal. The waveform repeated consistently, defying expectations of what space beyond the heliopause should look like. To understand why this is so significant, it's important to consider the nature of the interstellar medium. Until now, scientists believed this region to be largely homogeneous, mostly a cold, diffuse mix of hydrogen and helium atoms, interspersed with occasional cosmic rays and magnetic fields too weak to show significant structure. In essence, it was considered an empty, quiet environment, but Voyager 1's recent findings suggest otherwise. What the probe appears to have encountered is a coherent, oscillating wave, a repeating structure in the plasma. According to experts, this wave stretches across hundreds of millions of kilometers, and its pattern is not random. Instead, it exhibits a kind of regularity that scientists describe as coherent, meaning that the structure maintains its form across both time and distance. Initially, this discovery was met with skepticism. Some engineers and mission scientists assumed the data might be flawed, perhaps due to radiation damage to the probe's instruments. After all, Voyager 1 has been traveling through space for almost 50 years, exposed to cosmic rays and extreme temperatures. Hardware malfunctions are not uncommon in such aging systems. However, after thorough cross-checking and validation, NASA's team confirmed that the signals were genuine. The data didn't appear to be the result of a sensor error or noise from deep space interference. Rather, it pointed to a real, observable structure in the interstellar plasma. This breakthrough has wide-ranging implications. If space beyond the solar system isn't as uniform as previously thought, it means that our current models of interstellar physics may be incomplete. The idea that matter and energy behave in a more complex and organized way than expected opens up many new lines of inquiry. For now, what's clear is that Voyager 1 has once again made a discovery that pushes the boundaries of our understanding. The consistent wave patterns it has recorded challenge decades-old assumptions and raise new questions about the nature of space itself. NASA hasn't released definitive conclusions yet. There's still a lot of work to do in interpreting the data. Teams around the world, from plasma physicists to astrophysicists, are analyzing the waveforms to try and understand what kind of phenomenon could create such an effect in an area once thought to be mostly empty. There are several theories being considered. Some researchers suggest that the wave could be the result of natural events like distant supernovae that once sent shock waves through the galaxy, leaving behind subtle traces that linger for millennia. Others think it could be due to interactions between magnetic fields from different parts of the galaxy, forming standing waves in the plasma, similar to how ripples form on the surface of a pond when disturbed. A more speculative group of researchers has floated the idea that the wave may not be natural at all. While this theory is still fringe and no credible evidence supports it yet, some scientists have begun to consider whether the structured waveforms could be a form of signal, perhaps even intentionally produced. It's a bold idea, and most remain cautious. Still, the regularity of the pattern has prompted some to look beyond conventional explanations. Whether or not these waves are artificial, what Voyager 1 has detected is a major scientific event. The probe has passed through a region of space that appears to be more structured and dynamic than expected. This is particularly surprising given that most theories about interstellar space have operated on assumptions of simplicity and randomness. At a distance of more than 15 billion miles from Earth, Voyager 1 continues to defy expectations. It was never designed to explore interstellar space. Its mission was initially focused on flybys of Jupiter and Saturn, but its continued functionality decades later has allowed it to become our first emissary to the stars. It's providing insights no one could have predicted when it was launched during the Cold War era. In recent years, public interest in the Voyager missions had largely quieted. Many assumed the spacecraft would soon fall silent. But this new data has brought Voyager 1 back into the spotlight. It's a reminder that even the oldest tools, if well built and guided with care, can still offer new knowledge, and sometimes they do so in ways that reshape how we think about the universe. The scientific community is responding with a mix of excitement and caution. Several institutions have already begun reviewing archival data from past missions like Pioneer 10 and 11 to see if there are any similar patterns that may have been overlooked. Others are proposing new missions to follow up on Voyager 1's findings, this time with modern instruments capable of higher resolution measurements. While it's still too early to say what exactly Voyager 1 has uncovered, there's no denying that it has once again changed the conversation around space exploration. What began as a mission to the outer planets has become one of the most unexpected and long-lasting experiments in the history of science. For decades, researchers believed the interstellar medium was a largely uniform environment, cold, diffuse, and without much structure. It was thought to be a quiet backdrop to the louder, more energetic regions around stars, black holes, and nebulae. In this view, interstellar space served mainly as a transitional zone, a sort of cosmic no man's land where not much happened. But Voyager 1's new data challenges that idea directly. The plasma waveforms it has recorded are not random. They show a level of organization that was not expected in such a distant and sparse environment. While space within our solar system is influenced by the sun's magnetic field and solar wind, Voyager 1 is now far beyond that influence. It passed through the heliopause, the boundary where the solar wind meets the interstellar medium, back in 2012. Since then, it has been operating in a region that is considered purely interstellar, unaffected by the direct presence of our star. What makes these findings particularly interesting is the way the waveforms behave. Scientists analyzing the data have noted a consistent pattern in the frequency and amplitude of the plasma oscillations. These are not bursts or sporadic signals, but something more stable and repetitive. The signals resemble standing waves, oscillations that maintain a fixed pattern over time. In physics, standing waves are often found in environments where energy is being reflected or constrained, such as the vibrations on a stringed instrument or the ripples in a contained pool of water. Applying that idea to interstellar space is remarkable. It suggests there could be structures or boundaries in the plasma that allow these waves to form and remain coherent. This challenges the belief that interstellar space is entirely open and unbounded. It hints at the presence of forces or conditions that guide the behavior of plasma across extremely large distances. Several theories are being considered to explain how such a wave could form. One possibility is that the wave is the result of a magnetic reconnection event, a process where magnetic field lines from different regions snap together and release energy. This phenomenon has been observed in our own solar system, particularly around the sun, where it plays a role in solar flares. If similar events can happen in interstellar space, they could be responsible for the energy needed to produce the waves Voyager 1 has detected. Another potential explanation involves the remnants of ancient supernovae. When a star explodes, it sends shock waves through the surrounding space, disturbing the local magnetic fields and scattering heavy elements into the galaxy. These events are known to create ripples and disturbances in the interstellar medium. It's possible that Voyager 1 has passed through one such remnant, a faint echo of a cataclysmic event that happened thousands or even millions of years ago. There is also the idea that the wave is part of a much larger structure, possibly connected to the magnetic fields that permeate our galaxy. The Milky Way contains vast magnetic structures that we are only beginning to understand. If these fields form patterns or filaments, they could shape the behavior of plasma in ways we hadn't previously considered. Voyager 1's wave detection might be just one example of a broader and more intricate network of interactions stretching across the galaxy. While these natural explanations are still being studied, some scientists have begun to ask more speculative questions. The regularity of the waveforms has led to a small but growing interest in the idea that the signal might be artificial, although there is no direct evidence to support this. The concept is not entirely without precedent. In the search for extraterrestrial intelligence, or SETI, one of the major challenges has been deciding what kind of signals to look for. Most searches have focused on radio waves or light pulses, forms of communication we know how to detect and interpret. But what if an advanced civilization used a different method? Instead of broadcasting with light or radio, it might encode information into the structure of space itself. Plasma is an excellent medium for carrying energy in waveforms. It reacts to electromagnetic forces and can maintain oscillations over long distances. Some researchers have proposed that modulating plasma waves could be a subtle but effective way to send signals across interstellar distance. If such a method were used, it might look very much like what Voyager 1 has just detected. It's important to stress that this idea remains speculative. The scientific consensus is still firmly rooted in natural explanations, but even without invoking artificial origins, the wave Voyager 1 encountered has massive implications. It challenges how we understand the distribution of energy in space, and it suggests that the interstellar medium is far more dynamic than previously thought. If these kinds of structures are common in the galaxy, they could influence many other cosmic processes. For example, they might affect how cosmic rays travel through space. Cosmic rays are high-energy particles that originate from outside the solar system and sometimes from distant galaxies. Their paths are shaped by magnetic fields and plasma environments. If structured waves exist throughout the interstellar medium, they might help explain why cosmic rays arrive at Earth in uneven patterns or with unexpected variations in energy. The discovery also has implications for star formation. Stars are born in dense clouds of gas and dust where gravity pulls material together until nuclear fusion ignites. If interstellar plasma contains oscillating waves or structured magnetic fields, they might play a role in shaping these clouds, influencing where and how stars form. It opens up a new line of inquiry into the early stages of stellar evolution and how large-scale galactic forces shape individual star system. From a technological standpoint, the findings are equally significant. If plasma waves can maintain coherence over long distances, they might one day be harnessed for space travel or communication. Some researchers have begun to consider whether spacecraft could be designed to interact with these waves, much like a sailboat catches the wind. This idea is still in its early stages, but the basic principle is intriguing. It would mean using the natural properties of space itself as a tool for movement or data transmission. Voyager 1's detection of structured plasma waves has effectively opened a new frontier in astrophysics. It's not just a discovery, it's a starting point. Scientists are now working to determine how widespread this phenomenon might be. They are reviewing data from Voyager 2, which is also in interstellar space but on a different trajectory. So far, Voyager 2 hasn't recorded the same wave patterns, which could mean the structures are localized or that the detection depends on the angle or sensitivity of the instruments. Researchers are also examining data from older missions like Pioneer 10 and 11 in case they missed subtle signals that now make more sense in light of Voyager 1's findings. Additionally, new missions are being proposed to specifically study the interstellar medium with modern instruments capable of detecting plasma behavior in much greater detail. This new wave of exploration is being supported by a growing interest in interdisciplinary research. Plasma physicists, astrophysicists, computer modelers, and even linguists are now involved in analyzing the Voyager data. Everyone is asking variations of the same question. What exactly is this wave, and what does it mean for our understanding of the universe? No clear answers have emerged yet, but the excitement is undeniable. A probe launched nearly 50 years ago is now at the center of one of the most compelling scientific mysteries in recent memory. The structured wave it has found challenges long-held ideas about the simplicity of space and suggests a level of complexity that we are only beginning to uncover. Voyager 1's journey into interstellar space was never supposed to yield this kind of data, but its continued operation and the unexpected nature of its findings has reminded scientists of a timeless truth. The universe still holds surprises. Even in places thought to be silent and empty, there may be order, structure, and perhaps something more. The structured oscillations found in interstellar plasma have already begun to influence how scientists model the space between stars. Plasma physicists, for instance, are now rethinking the way charged particles behave in low-density environments. While plasma is a well-studied state of matter, often referred to as the fourth state alongside solids, liquids, and gases, our understanding of it in interstellar conditions has been relatively limited. Much of what we know about plasma dynamics comes from experiments on Earth or observations within our own solar system, where the density, temperature, and magnetic fields are very different from what Voyager 1 is now exploring. With this new data, researchers are refining existing models and building new simulations that attempt to reproduce the waveforms Voyager 1 encountered. These simulations help test whether the observed structures could arise naturally through known processes, or if they suggest the presence of factors not yet accounted for. The goal is to understand what conditions would allow plasma waves to form, maintain coherence, and possibly interact with their surroundings over such vast distances. Signal analysts and data scientists are also becoming more involved. The regularity and layered nature of the waveforms have drawn comparisons to patterns seen in artificial systems, like audio signals or compressed data files. While there's no evidence that the signal is artificial, its characteristics are drawing interest from those who study communication theory and information encoding. These experts are applying tools from their own disciplines to try to identify hidden structures within the signal. Are the oscillations purely the result of physical forces, or do they suggest some kind of embedded information, however rudimentary? Even linguists and semioticians, scholars who study symbols in communication, have started to explore what it would mean if the wave carried a message of any kind. This may sound speculative, but the idea is rooted in real questions faced by researchers working in the field of SETI. For decades, one of the biggest challenges has been knowing what to look for if intelligent life exists elsewhere in the galaxy. How would it communicate? Would it use light, radio waves, or something entirely different? If a civilization had discovered how to embed information in the fabric of space itself, using plasma as a medium, then we might have been listening for the wrong kind of signal all along. This shift in thinking has prompted some institutions to start re-examining previously gathered data with fresh eyes. Projects are being proposed to develop new types of detectors, ones capable of mapping plasma oscillations with greater precision and over a wider range of frequencies. These instruments could be mounted on future deep space probes or even adapted for Earth-based observatories, depending on the phenomenon they aim to detect. In addition to driving scientific research, Voyager 1's discovery has begun to influence technological design. Engineers and mission planners are now considering how future spacecraft might be built to better interact with or even take advantage of the interstellar environment. One idea gaining interest is the concept of plasma-based propulsion. If coherent plasma waves exist throughout space, could a probe be designed to ride those waves in the same way that a surfer rides ocean swells? This wouldn't be traditional propulsion, powered by fuel or ion drives, but a new kind of motion enabled by tapping into the natural structure of the medium itself. This idea is still in the early stages, and practical implementation would require significant breakthroughs in materials science and wave dynamics. Still, it represents a new way of thinking about space travel, using the environment as a tool rather than something to be resisted or overcome. It's an approach inspired directly by the kind of data Voyager 1 is now sending home. Navigation is another area where Voyager's findings might make a difference. Just as early sailors learned to read the stars, ocean currents, and wind patterns to guide their journeys, future interstellar explorers might one day rely on the structure of plasma waves to chart a course. If these waves are widespread and stable, they could serve as reference points in the vastness of space. By analyzing the frequency and amplitude of local plasma oscillations, a spacecraft might determine its position relative to known wave zones, much like GPS relies on satellite signals today. The influence of this discovery isn't limited to science and technology. Across the world, artists, writers, educators, and philosophers have been captivated by the idea that the space between stars is not silent or empty, but active and structured. It changes how we think about isolation in the universe. For centuries, the void between celestial bodies has been seen as a symbol of emptiness and distance, a reminder of how small and alone we might be. But now, it seems that even the most remote corners of space have their own rhythms, their own subtle forms of order. This has inspired new creative projects, from visual art installations that represent the waveforms as kinetic sculptures to sound-based works that turn the oscillations into music. Museums and science centers are developing exhibits that allow visitors to hear the waves, translating frequency data into audible tones. These public-facing efforts help make abstract data feel tangible and relatable, fostering a sense of connection with the cosmos that goes beyond equations and measurement. In classrooms and universities, educators are beginning to update how they teach about the interstellar medium. Until now, most textbooks presented it as a mostly static, inert region. Voyager's discovery introduces a more dynamic perspective, one that includes wave activity, potential interactions with distant cosmic events, and the idea that information may be flowing through the galaxy in ways we hadn't imagined. It's not just about learning new facts, it's about changing the framework through which we understand the space beyond our solar system. There's also a growing philosophical dimension to the discovery. If interstellar space contains organized, long-lasting structures, it raises questions about the nature of the universe itself. Some researchers are exploring the idea that these plasma waves could act like a kind of memory, a record of cosmic history. Just as tree rings or sediment layers on Earth capture environmental changes over time, perhaps the interstellar medium preserves traces of supernovae, galactic collisions, or other large-scale events. Voyager 1 may have passed through such a record without even knowing it, offering us a glimpse into processes that happened long before our planet existed. Others take it a step further, wondering whether these structures suggest an underlying order to the galaxy, a kind of cosmic architecture shaped by forces we don't yet fully understand. If magnetic fields and plasma waves are arranged in a meaningful way, then the galaxy might not be as chaotic as we once thought. It could be governed by patterns, cycles, and relationships that are only now beginning to come into view. This line of thinking doesn't necessarily imply intelligent design. Nature itself can produce complex, organized systems through entirely natural processes. But it does mean that space is more than just a backdrop. It's an active, evolving system that may influence everything from how stars form to how information travels across the universe. All of this adds a new layer of meaning to Voyager 1's mission. When it launched in 1977, it carried a golden record, an audio-visual message from Earth intended for any intelligent beings who might one day find it. At the time, the idea of such contact was highly speculative, and still is. But now, nearly 50 years later, Voyager has received a kind of message itself. Whether that message is natural or not, it has changed the way we think about the space between stars. The story of Voyager 1 has always been one of endurance and surprise. Its instruments, designed in a different era, continue to operate well beyond their intended lifespan, and its discoveries keep challenging our assumptions. The structured plasma waves it has detected are the latest example of this legacy, a quiet, unexpected signal that is now echoing across the sciences, the arts, and the public imagination. The main priority now is confirmation. Voyager 1's data is compelling, but to fully understand what it has encountered, scientists need additional points of reference. Voyager 2, which is also in interstellar space, has so far not detected the same structured waveforms. That doesn't mean they aren't present. It could simply be a matter of orientation, timing, or instrument sensitivity. And like Voyager 1, which appears to have passed directly through one of these coherent plasma regions, Voyager 2 may be on a trajectory that skirts around them or intersects them at a different angle. This discrepancy has become a key focus of current research. If these plasma wave zones exist throughout interstellar space, identifying their distribution and structure will be critical. Scientists have started proposing methods to detect them indirectly, including reanalyzing data from past missions like Pioneer 10 and 11, and developing new space probes equipped with more sensitive instruments specifically designed to measure plasma dynamics and magnetic fields at very fine resolution. In the meantime, researchers are also exploring Earth-based strategies. Although we can't directly measure interstellar plasma from our planet, certain cosmic events and phenomena like fast radio bursts, cosmic background radiation distortions, and gravitational lensing might interact with plasma structures in detectable ways. By correlating anomalies in these signals with Voyager 1's data, scientists hope to identify similar patterns elsewhere in the galaxy, allowing them to begin mapping the presence of coherent waveforms across much larger scales. One of the more intriguing aspects of this discovery is how it might influence our understanding of star formation. Stars are born in dense regions of interstellar gas and dust known as molecular clouds. These clouds are already known to be shaped by magnetic fields and shockwaves. If large-scale oscillatory structures like the ones Voyager 1 detected exist in the wider interstellar medium, they might also play a role in compressing or stirring these clouds in a way that triggers gravitational collapse, the first step in the birth of a star. In this context, Voyager 1 may not have just encountered a plasma wave, but a remnant of stellar genesis frozen in space for millennia. Another area now gaining serious attention is the possibility of energy harvesting in deep space. Traditionally, spacecraft rely on solar panels, onboard fuel, or radioactive sources to generate power. But if space itself contains organized regions of oscillating energy, could a future probe be designed to tap into that energy directly? Early experiments in plasma wave harvesting carried out in laboratory conditions on Earth have shown that under the right circumstances, it is possible to convert low-frequency plasma vibrations into small amounts of electrical energy. The concept is far from being mission-ready, but Voyager's discovery has given it renewed credibility and relevance. Even more speculative is the idea of interstellar plasma waves being used as a medium for data transmission. In this scenario, the waves themselves wouldn't just be natural fluctuations, they could act as carriers of complex, layered information. Much like how modern communication systems use different frequencies to encode audio, video, and metadata into a single signal, it might be possible that some forms of information, natural or otherwise, are traveling through space encoded in waveform structures. Voyager 1's readings have shown overlapping cycles within the wave patterns, each moving at a different rate, yet maintaining coherence over distance. That level of structure has caused some researchers to explore models of waveform-based data encoding, an area now being referred to as interstellar signal topology. This idea isn't necessarily about aliens sending us messages. Rather, it suggests that the universe itself might carry information in ways we hadn't considered. Physical systems often retain the imprint of past events, whether it's the ripple from a distant explosion or the subtle shift of particles reacting to gravitational forces. Space may act as a kind of information field, storing echoes of what has happened across vast stretches of time and distance. This has led some scientists and philosophers to consider the interstellar medium as a kind of memory space, one not recorded in light or matter, but in the energy fields and oscillations that quietly fill the void between stars. If this concept holds, then the plasma waves Voyager 1 encountered might represent something more than just a physical structure. They could be remnants of galactic history, still vibrating in the cold, thin fabric of space. The potential scientific value of these waveforms is enormous. For those studying the early universe, understanding how such structures form and persist could offer insights into the conditions under which the Milky Way itself took shape. If the waves are ancient and stable, they might be the result of early galactic processes, like the rotation of spiral arms, the passage of black holes, or even remnants of dark matter interactions. These possibilities remain unproven, but they illustrate how one data point gathered by a spacecraft powered by less electricity than a mobile phone charger can lead to far-reaching questions. Voyager 1's data is also inspiring new ideas about space exploration itself. Just as mariners once navigated the seas by reading the winds and the stars, future spacecraft might navigate interstellar space by following the structure of plasma waves. If coherent resonance zones exist and can be mapped, they could serve as reference points, natural markers in a space that has long seemed directionless. This could revolutionize how deep space missions are planned, offering a new form of passive navigation guided not by artificial signals, but by the natural texture of the cosmos. The idea of plasma-assisted propulsion is also being explored. Although currently theoretical, it imagines a spacecraft designed to interact with oscillating plasma fields in such a way that it gains momentum, much like a surfer catches a wave. If the interstellar medium has large-scale electromagnetic structure, this kind of propulsion could offer a means of sustained motion without the need for traditional engines or fuel. Such a development would be transformative not only in terms of efficiency, but in how we approach the challenge of crossing vast interstellar distances. Culturally, Voyager 1's discovery has resonated in ways that few scientific findings do. It has reminded people around the world that space is not empty or inert. It is active, vibrant, and perhaps more connected than we once thought. It challenges the long-held image of the void as a place of silence, replacing it with something more dynamic and alive. The idea that signals or rhythms might be pulsing quietly through the galaxy adds a sense of mystery and beauty to our understanding of the universe. This discovery has also reignited interest in SETI. The traditional approach to searching for extraterrestrial intelligence has focused on detecting deliberate radio signals or light pulses. But what if intelligent life doesn't communicate that way? What if it uses methods we've never considered, like modulating energy into the medium of space itself? While this remains purely speculative, Voyager 1's findings have encouraged researchers to widen the scope of their search, developing instruments that can detect patterns in plasma waves or other less obvious carriers of information. At the same time, artists, musicians, and writers have begun interpreting the data in their own ways. Some have turned the oscillations into soundscapes. Others have created visualizations or animations that imagine what it might look like to move through a region of structured plasma. In classrooms, educators are using the story of Voyager 1 to illustrate not only the principles of science, but the importance of patience, persistence, and curiosity. As Voyager 1 continues its slow journey outward, its instruments are expected to run out of power within the next few years. When that happens, the spacecraft will fall silent for good. But its legacy will continue. The information it has sent back has already reshaped the way we think about interstellar space. It has launched new questions, sparked cross-disciplinary research, and opened a new chapter in our quest to understand the universe. Perhaps the most profound part of this story is that Voyager 1 wasn't meant to do any of this. It was never designed to study interstellar plasma or detect coherent wave structures millions of kilometers wide. It was built to fly past Jupiter and Saturn and then drift into the void. Yet by simply continuing on its path, by staying operational and sending back data, it has managed to stumble into one of the most surprising discoveries of recent decades. This reminds us that exploration often works this way. Great discoveries sometimes come not through dramatic moments, but through steady, determined observation. Voyager 1 didn't find something by chance. It found something by continuing. In doing so, it has once again redefined what it means to explore the unknown.